Now let's go on and talk about Newton's third law. For Newton's third law, it's called the action and reaction law. For every action, there is, and you've heard of this before, an equal and opposite reaction. What that means is that in every interaction, there's a pair of forces acting on the two interacting objects. The size of the forces on the first object equal the size of the forces on the second object. Okay, let's talk about this and break this down a little bit. Notice that the action force and reaction force act on the same two objects, but there have to be two. They have the same magnitude and they are oppositely directed. Okay, so here I have my table, or floor in this case. I have my box. I have the force of gravity acting downwards and the normal force acting upwards, and they should be the same length. Okay, I made my gravity a little bit longer. It was looking a little short. Okay, let's talk a little bit more about what the normal force is. The normal force is the support force from the floor acting on the box. Because again, if it wasn't there, then the box would go crashing through. So the floor is supporting the box and giving it a little bit of force in the upward direction. The gravitational force is the force of gravity on the box. Well, yeah, it's a force of gravity on the box which is acting upon the floor. So this box now is pushing on the floor, and the floor is pushing on the box. And so they are pushing on each other. That means that they are an action-reaction pair. So the force of the box on the floor and the force of the floor on the box are an action-reaction pair. They are the same magnitude, same length, oppositely directed, and they are on two objects upon each other. That is an action-reaction pair. And so, as we said a second ago, these are equal and opposite. They are an action-reaction pair. Okay, this time it's going to seem like just a semantic difference right now. And then later we might be able to explain it a little bit more in depth. But what if we look at only the forces on the box? And so I kind of alluded to this a minute ago. So we have the force of gravity of the Earth, basically, pushing down upon the box. And then we have the normal force pushing up on the box from the floor. So we have the gravitational force pushing on the box, and we have the normal force pushing on the box. Okay, what can we say about the two forces in our new diagram? We've changed up the diagram. It looks different. Well, both forces are acting on the box. They are not an action-reaction pair because they're only acting on the box. And so the question might be, well, then what is the reaction force to the gravitational force on the box? And that would be the force that the box exerts on Earth. So that box actually does exert a force upon the Earth. It's minuscule in comparison, right? Because the Earth is huge and the box is tiny. But there is a force of the box on the Earth. So, do action-reaction pair forces have to be contact forces? Oh no, this is an interesting thing. Hang on, let's wrap up what we've done here. First of all, like I said, it's just a little bit of semantics. And it's also a little bit how I drew my vectors. I don't love how I drew them this way. But basically what we're saying is these are not an action-reaction pair because they're both acting on the box. In order for it to be an action-reaction pair, we would need the box to be acting on something else, which it is, but we didn't talk about this example, okay? Now let's talk about this question D. Do action-reaction pair forces have to be contact forces? Why or why not? You really have to, no pun intended, think outside the box here. Let's think of something tiny, like a molecule or an electron. Or maybe something a little bit bigger than that, like a piece of paper shard, like just a little tiny piece of paper shard. Do action-reaction pair forces have to be contact forces? Why or why not? Are there any other forces that you can think of that might suspend something like a molecule or a piece of paper. Could we suspend this piece of paper, teeny tiny little piece of paper, could we suspend it in the air? We could. We could. It would look like a magic trick, but it's not. It's physics. There are other forces other than just contact forces. So when we talk about contact forces, we're talking about like a push or a pull. Well, no. Gravity, we can't see that. Sound. Have you ever been to some of those museums where they have sand and they've got the sound waves going through the sand? Okay. Waves, various, whatever kind of wave you want to think of. Magnetic forces, electrical forces. So like with the little piece of paper I'm talking about, like we will work with electrostatics later in the year, and we can get things to kind of suspend in the air with electrostatics, with static electricity. And you've seen that before. Like you can rub a balloon on someone's head and it'll just stay there, right? That's static electricity. You could say that's a contact force because you touched it. But even though like you've seen stuff, maybe hold it close to your hair and it pulls your hair out even though it's not touching it, right? Okay. All right, that is the end of Newton's third law. Next video will be about Newton's second law.